Let's go ahead and take a look. All right. One of the things to remember in this chapter, right, is you're going to be making an enol or an enolate. So the first thing you should do, especially on the homework that's online and the exams and quizzes that'll be online, is get a piece of paper and write things down, right? So the first thing you want to do is draw your enolate, right? That's what this chapter is about, right? So draw your enolate. And then once you have your enolate, then you can think about what you're going to do with it, right? And remember that it's always going to be the alpha carbon, right? So this carbon here is going to be reacting. So if you work through that, know that you're going to make an enolate, and it's going to be the alpha position that you're going to be focusing on, right? It's going to help you get the right answer. Okay, so this is just alkylation of the alpha carbon. LDA gives us quantitative enolate formation, so we don't have to worry about it reacting with itself. Okay, questions about this one? And the second one, again, form your enolate, right? So in this case, I've got a reversible process. So I'm going to form this enolate, again, going to the alpha position. So I know that's where I'm going to react, right? And this is going to react with itself. And I know that because this is reversible, right? I'm not using LDA or something like sodium hydride. I'm using a weaker base. So now I've got some of that ester to react with it. And so again, think about what's happening. The alpha carbon is attacking the electrophilic carbon. And I'm gonna go down because we're not quite done yet. Right, so I formed that. And then here, right, now the methoxide is a decent leaving group. So that leaves, and I end up with the carbonyl at that position, right? And now, since that's a dicarbonyl, what we just need to do is protonate, because remember, the methoxide that comes off is a good base and could pull that proton, right? So I use the H3O plus. Here I've given you a hint. When it says dilute, is this going to hydrolyze? No. So we're going to end up with we're not going to end up with the acid, we're going to end up with the ester, right? So all we do here is protonate because I'd pull off that last proton. Okay, questions about this one? If I had seen a strong acid, this could have hydrolyzed to the acid, carboxylic acid. If I had seen acid and heat, because this is a 1,3-dicarbonyl, I could have decarboxylated, right? Because I could have hydrolyzed to the acid. So let's show that. So few treatments here, right? So we do the methoxide, but in this case, let's say H2SO4 and water, right? Trying to indicate that it's strong. In this case, I get the acid. If I did the same reaction, starting with the same starting material, but now put H3O plus and heat, right? I'll decarboxylate and I'll end up with this ketone. Questions? Okay, so we're moving into chapter 22, amines, but we have a few more quizzes to get out of the way. So although our exam 3 is on December 2nd, that would put our quiz on Thanksgiving, and we won't do that, but we will have quiz 3 next Tuesday. Okay, similar format to last time. Okay. You'll have after the class until pretty late at night. So if you're planning to travel, just take enough time to take the 15-minute quiz. We will have class on Tuesday next week. Okay. Questions about exam 3 or exam or November? Our last quiz, we do have a quiz 4. We'll probably do that the Wednesday. That's the last day that we can have an assignment in class. We'll do that Wednesday. And again, that one will be more of a review for the final exam. Okay, so, and then the final exam will be December 14th. Same process. If you want to come here, so you'll have a quiet place to work, that's fine. If you want to take it from home, it'll be online. Okay. All of the online homework that has been completed is now up. You should see the grade adjustment. So some of you might notice that you're above 5 points. That's what I did with the grade adjustment. And then I adjusted exam 1. So you should have noticed that. If you have any questions about exam 1, let me know, because I believe I caught all of the adjustments for the orthopara problems, the problems that we solved. Okay. In this week's homework, there were a couple problems. One of them, and I may not get these totally right, but the answers will be right. LDA minus 78 degrees Celsius, followed by, this bromide. This is the answer, and several people have shown this as the answer, and it's not grading it correctly. So I'll turn this one in, but with the LDA minus 78, it should go to the opposite side, the kinetic side, and this should be your answer. So a couple of people sent me those, and this is what it should be. There's another one that's not being graded correctly. It has 2 methyls on one side, meaning I only have one more, and I think this one is LDA followed by, I think that methyl bromide. This one should give you this, and again, it doesn't appear to be grading it correctly. So if you're having trouble with either of those two, know that I'm aware of them, and I'll do like I did last time. I'll go through and see who was assigned those problems, and I'll make a grade adjustment after the fact. But if you're getting these 2 answers, those are the right answers. Okay. The online homework system is not grading it correctly. Right. Any questions about quiz 3 next Tuesday? Okay. So let's move into amines. By this time in the semester, and actually by the end of the course, you've seen almost all of these things before, but it is to go through. So you've seen amines. We've been using these for a while. And it's important to understand some different terminology, right? This is called a primary amine, right? And here we're focused on the nitrogen, right? So how many carbons are attached to the nitrogen? How many carbons are attached to the nitrogen, right? So when we're looking at amines for this classification system, we're looking at the nitrogen, not the carbons. And then because it has a lone pair, I can go all the way to a quaternary salt. And it's called a quaternary salt because if you put 4 carbons on there, right, this becomes positive, right? So I'm going to have some kind of negative on there. So quaternary ammonium or quaternary salt. Okay, this is going to be important because it turns out that you know, lots of the things you're going to looking at is primary amines, and when we look at synthesis, there's some strategies that work well for primary amines and some that don't, right? And then there's some where you want to combine mechanisms so that you can turn a primary amine into a secondary amine and so forth. The base reactivities, the first thing to think about with amines is that they are bases. And often, if you see a biological system and you see an amine in it, this is often what the amine is doing, right? It's going to act as a base and it's going to abstract a proton. So the amine is going to pick up that proton, right, to give us the salt. So nitrogens are in a lot of biological systems, and this tends to be one of the reasons that you see those. So if you see a biological structure, that means, especially in an enzyme, that probably means that you've got a proton transfer going on, and that nitrogen is going to be helping with that proton transfer and that mechanism. So when you get to biochemistry, looking at mechanisms and how processes work, that's one thing to be thinking about with the nitrogen. The other is that these can be nucleophiles, right? So if we look at the nitrogen, it's got the lone pair. Negative goes there, right? Kicks off the iodine. And now we have a bond to that methyl group. And in this case, right, we potentially could add a base and lose a proton. Besides the straightforward amines, remember we have a couple of other groups, such as the aromatics, like the aniline, right? That's an amine. We've got the heterocyclics, like pyridine. Right? And then we have the pyrrole. And you'll see pyridine and pyrrole processes in different biological systems. Okay. So base and nucleophile is what we're going to be reacting with most often. Remember that we have several different other groups. Okay, if we look at nomenclature, this one could be known as ethylamine, or also ethane amine. Oop, I dropped the E. Right, so we can use the amine as actually the suffix. So if you could think about alcohols, naming as the OL, right here, we're just going to drop the OL and add the amine. The common name, ethylamine, right? We could have methylamine. We've seen those before. The difference there is we're using the YL versus the AN. Okay. So the IUPAC is just like we would name our alcohols or our other groups. Now, we often go with oxidation state, which means that in this case, the alcohol is going to have preference over the amine, which means the root of this is going to be propanol, right? One propanol, and then the nitrogen then becomes a side group, and as a side group, this is the amino, right? So the amino is our side group name. So just like hydroxy was our side group for alcohols, amino is going to be our side group name for amines. So pretty straightforward. The other thing to remember on amines, and we've seen this in a couple of places before, but to bring it back to your attention, if I have a secondary or tertiary or even quaternary amine, right, I need to say what's attached to the amine. So in this case, this is going to be 2-pentamine, right? So that's that. But then I have the 2 methyls, and that becomes N,N-dimethyl. If we looked at something like this would be a dianamine. And so in this case, we have 1, 2, 3, 4, 5, 6, 7. So it's going to be heptan diamine. And then our numbers here are 2, 3, 4, 5. But notice now I have a methyl and an ethyl, right? So the methyl goes second. That becomes an N prime. So it's going to be N-ethyl N prime. Let me make that look a little better. N prime methyl 2,5 heptane diamine. Okay, here, this is the N prime and this is the N, and that's because of the 2 and the 5, right? So the preference will go to the lowest number. So the 2 on the first nitrogen means that I'm going to name it as the N. So you could have N, N prime, N double prime, N triple prime, so forth. So instead of using numbers, you change your nitrogen prime. Okay, questions about nomenclature? Pretty straightforward, not much difference than what you've seen before. Okay, if we think about amines, if we look at just the loss of a proton, right? We know that the pKa of the amine here is around 35, 36. But more importantly, is not the basicity of extraction of that proton, but what happens if the nitrogen is used as, let's do it this way. What if that proton is being used not as a base? I mean, not as an acid, but a base. right? And then this becomes the pKa over here. And in general, these are going to be in the range of 9 to 10. So again, since amines are most often used as bases, right? What we'll be looking at is if it was used as a base, where is the pKa of the conjugate acid that's formed versus the base? So if we look at triethylamine, with a, let's say, acetic acid here, if you want to take shorthand, you can just put ET there instead of showing the whole thing. And so if we look at our pKa's here, the pKa of the acid here we know is about 4.76 or is 4.76. But then over here, when we look at the protonated triethylamine, right, we end up with 10.76. So if we look at these versus, like, say, alcohol deprotonating something or met water deprotonating something, those would be much more acidic, right? So the pKa's of those would be down in the range of 0. Here we're looking at around 10. The other areas that you want to watch for is the pKa of our amines, our anilines. So again, if we pick up a proton, okay, this has a pKa of 4.6, right? We can delocalize those electrons, stabilize this. So it's more acidic than the regular amine. And for pyridine, we get a pKa 5.3, right? So amine is a better base than the aniline and is a better base than the pyridine. We use pyridine as a base because pyridine is also not nucleophilic, right? Where an amine would be nucleophilic. Okay, questions about pKa's? Preparation of amines. From nitriles. Nitrile is a good nucleophile, right? So we can do an SN2 style reaction to get the nitrile addition. And then we can reduce that with lithium aluminum hydride, followed by water. open this up a little bit. So a couple of things with the nitrile process. We've added one carbon. Okay, that's important because sometimes it's difficult to just add a carbon, okay, especially if you add a carbon with functionality. And then second, this is making a primary amine. So I would use the nitrile if it needed to be make a secondary or a tertiary amine, but this will make the primary amine. So I add a carbon, make the primary amine. Again, this is review. We've seen these reactions before, but we haven't focused on these as a way to make an amine. And again, this works for most things, but we have to remember that this is an SN2 style reaction, so that our electrophile needs to be an SN2 style reactant. Okay. We can also make amines from carboxylic acids. Now, it may be obvious, but just to review, I couldn't take, if I took carboxylic acid and added the amine, what I'd end up with is the carboxylate and the ammonium, right? So here the amine acts as a base, so I'm not going to get a substitution. But if I take that carboxylic acid and convert it to the chloride, right, then I can make the amide, and then I can reduce the amide with lithium aluminum hydride and water. To make the amine. And again, in this case, right, we're going to make a primary amine. If we wanted to make a secondary or tertiary amine, we would need to do that in the conversion in the first step. So I could take the acid, add SOCl2 to make the chloride, and then here add let's say a secondary amine. To make the tertiary amine. So from the carboxylic acid could be used to make primary, secondary, tertiary amines. We just have to remember, if we're going to make the primary amine, we add ammonia. If we make the secondary amine, we add a primary amine. If we want to make the tertiary amine, we add a secondary amine. Okay, so you're adding one carbon each time you go up. And then the other one that we haven't seen in a while, and again, this is review. It hasn't been the focus, but These are review reactions. We didn't focus on making amines, but we've seen all these reactions. The other one that we didn't focus on was creating an anilines. And the aniline synthesis, the main reason that we do the nitration, unless you wanted to work in explosives, is to make the anilines. So you do the nitration. Again, this is a review reaction. We've seen this one. You make the nitro, and then you can either do a catalytic reduction with hydrogen and palladium on carbon, or another good catalyst. Palladium carbon is the one you see most often. Platinum will also work. Or you can take a metal and acid, followed by base. And here, the metals that work for this one are iron, tin, zinc, and tin chloride. All right, so you've got several metals. Iron is the one that you see that one a lot, iron and hydrochloric acid. Okay, you have to add the sodium in the second step here because the product of the acid first reaction would be the protonated form. So if we take this and react it with iron and HCl, the product of this reaction is going to be the protonated amine. Right. So therefore we add the sodium hydroxide to neutralize that and get back to the free amine. Now this free amine, a lot of times people talk about tobacco and anything they do to make it more addictive. Turns out that there's two. You have to treat tobacco to make it palatable. So you either have to treat it with alcohol, which is what you see, let's say, in the Cuban countries, and I mean Cuba and many other countries, or you treat it with lye. You treat it with a base. But if you treat it with a base, what you do is you actually form the free base. This is what's referred to as a free base. You have an ammonium complex, you hit it with a base, and it makes a free base. Now, the free base of the nicotine is more, will go into your bloodstream faster than the protonated form, right? And so the main difference between the tobaccos is that they're usually treated with a base solution. In the US production, and in some other countries, they use alcohol based. So you can actually get a faster hit. Same thing as free basing cocaine versus just regular cocaine. Free basing cocaine will go, all you do is you treat cocaine with lye, and all of a sudden it can make it much more potent because it's the same compound. All you're doing is making it get into the bloodstream faster. Our pseudo useless fact of the day. Okay, alkylation of amines. It is possible to alkylate amines. You know, these are good nucleophiles. So I can say nucleophile attacks electrophile, leaving group leaves. And then we can pull off a proton to get to the product. But if we look at our product here, if we look at that versus which of these two is going to be a better nucleophile? Well, if we think about what's happening, right? If we have through hyperconjugation, right? Which one of these is more stable? The first one or the second one? Well, because of hyperconjugation, right? The carbon on this one is more stable. If that one's more stable, which one of these is a better nucleophile? This one is a better nucleophile. We can get the same analysis from the pKa's, right? We can look at the pKa's of these two, right? So if we look at the ammonia versus the methylamine, if the methylamine is a better nucleophile, is it going to be easy to stop at this process? Or what is this going to do if I have methyl iodide around? This would react with the methyl iodide to add a second methyl. And so alkylation of amines is actually very difficult to stop. So what usually happens is you have this reacting with that, which makes a blob, which makes this methylamine, right? But that methylamine can react with more methyl iodide to make the dimethylamine, which can react with more methyl iodide and potentially even that can react to get to the quaternary. And then at the quaternary, right, it's not going to react any further. We've alkylated it all the way. Right? Because every time I add a methyl, I'm making the product more nucleophilic than the starting material. This is going to drive towards the quaternary, right? So it's easy to make quaternary amines from alkylation. It's hard to make primary amines. So if I really want to selectively make a primary or a secondary amine, straight alkylation by taking the nitrogen is not going to be the way to go, right? Because I'm going to be able to, every time I add a methyl, I'm making it more reactive. So sometimes you'll actually see processes where they'll take something like this, and then they'll add methyl iodide, and then they'll put some type of mild base like sodium or potassium carbonate. And what this does is go all the way to the fully quaternary salt. Okay. So since alkylation of amines is difficult to stop at a primary, then we need some ways to make primary amines. Primary amines are very common, right? We don't always want to go to the quaternary amine, but there are times where the quaternary amine is going to be important. We'll see that when we come back on Thursday. Okay, so we've already seen one way to make primary amines, but that method adds a carbon, right? So we can do the nitrile. So we could take the bromide, add the amine, okay, but as a carbon. So sometimes we may not want to add a carbon, but that will end up with a primary amine. One that'll add a nitrogen as a primary, but won't add a carbon is the azide synthesis. Probably haven't seen azide since last semester. You may have wondered why we had this funny N3 compound, right? These are really good nucleophiles. But then this azide can be reduced with hydrogen and a platinum and palladium, palladium on carbon or platinum, or with lithium aluminum hydride in water. I should have just done my arrows back. And this will only give primary amines. Okay, so I haven't added a carbon. I get the primary amine. Remember, the azide is this compound. So that reacts in an SN2 style, right? It's a really great nucleophile because it's linear. And then this can react with this aluminum hydride. Hydride attacks the first nitrogen, kicks the electrons back to the second nitrogen. And then these electrons go here, kicks these electrons back to that nitrogen. Gives me this negative plus then nitrogen N2. And then the last step is the proton from the water. To give us the primary amine. Okay, so nucleophilic attack, we saw that last year, right? Review. And then the hydride attacks the first nitrogen. And then we've seen this before where we get this decay and loss of the nitrogen, right, to give us N2. And then last step, we protonate that amide by adding water to give us the primary amine. Okay. So this one works really well, especially anytime that I have an SN2 style electrophile. And azides are good nucleophiles. They're not overly basic, so I don't have to worry about many side reactions. Another primary amine reaction is Gabriel synthesis. Gabriel synthesis uses a succinimide. So this is not N-bromosuccinimide, this is just succinimide. We add a base like potassium hydroxide. Then we add our electrophile. And then there's two different ways we could work that up. One of them is H3O plus. And we'll go through the steps on this one. So the N-succinimide becomes this dicarboxylic acid species, or succinimic acid, plus then we get the base, we get the protonated species. So we then would take our ammonium, treat it with a little bit of base to get it back to the free amine, the NH2. So what's happening? Let's show the whole mechanism. Okay, so we pull the proton. Okay. Now that nitrogen negative is delocalized to the carbonyls. Okay, so it's pretty stable, so it'll wait until we add our electrophile. So then we get backside attack. All right. So in an SN2 style reaction, right now we've got the carbon nitrogen bond formed. Then when we add the acid, we're going to get hydrolysis. This is an amide, but the hydrolysis is like an amide, and then the second part is an amide, right? So what we end up with is our diacid. Plus the protonated amine. Okay, so the acid followed by sodium hydroxide is one synthetic workup. The other one is to use a hydrazine. Similar process. We're going to start with the succinimide here. We're going to react it with the potassium hydroxide. Add our electrophile. But then in the last step, instead of adding an acid and then following it up with a base, we're going to add hydrazine, which is the NH2 compound. What this does is instead of hydrolyze it to the diacid, it substitutes the nitrogen, the hydrazine in for the nitrogen, kind of displacing it, giving us the NH2 without having to go through through the acid and then hydrolysis followed by the base. Okay. All right, questions about this one? So both of those are Gabriel synthesis. Now, Gabriel synthesis looks like a negative carbon loss, and in a research lab, it can be. Industrially, what they do is they take the either the dialcohol or the hydrazine, and they recover it, and they actually turn it back into N-succinimide, right? So if I add ammonia to that and heat, I can actually go back to the N-succinimide, so I can regenerate my starting material. Or in the hydrazine, all I have to do is really add heat, and I can get it to the starting material, right? So although it looks like this is pretty wasteful, especially with our climate in Scotland last week, this would be a huge carbon negative type reaction. But this compound industrially would be siphoned off, and it crystallizes really easily. It'd be siphoned off, and then I would add ammonia and heat and get it back to this one. So industrially, I can actually recycle this molecule. And so it'll just, you separate the two, you take it, you recycle it back into the reaction, and you're always regenerating this molecule by adding ammonia. Okay. So actually pretty straightforward synthesis, and it's easier to work with azide. Azide in high concentrations does have a tendency to be volatile. So both of those are primary amines, right? So those are focused on primary amines. This next one is going to be focused on, this next one is flexible to be primary, secondary, tertiary, right? So it can give us selectivity similar to what we did with our carboxylic acid going to the amine before. And this one is reductive amination. Reductive. So here, if we have a carbonyl, such as an aldehyde or ketone, react that with nitrogen, amine, right, with a trace acid. We could reduce the enamine, the imine, in this case, an imine, to the amine. We could also do that or there's a special reagent, and the special reagent allows us to do this all in one pot. So if we think about it, both of these reagents, the hydrogen and platinum or palladium, and then the sodium borohydride, we'd want to form the imine first, because sodium borohydride will react with the carbonyl, right? And so we don't want to do that. And the sodium, the ammonia and platinum, we wouldn't want around in the amine. But there is a special reagent. If I take the ketone, react that with the amine in the presence of sodium borohydride, the cyanoborohydride, with a trace acid, the cyanoborohydride will not, the sodium cyanoborohydride will not react with the carbonyl, okay? So now I've added a reducing agent that won't react with the carbonyl, which means that I can do this all in one pot. So I don't have to do it in multiple steps. So I don't have to make the imine and then reduce the imine. Okay, so the sodium, it's a special reagent, right? Don't put in the sodium borohydride, because sodium borohydride could reduce the carbonyl. But we can see here, this is made a primary amine. But I could take that same ketone, right, and now add a primary amine with the sodium cyanoborohydride, trace acid, right, and that'll make me a secondary amine. And I don't have to worry about getting any tertiary amine or any other reactions like I might with an alkylation. And I could take that and react it with a secondary amine. Again, same reactions with the cyanoborohydride. To get the tertiary amine. So this one's nice because it gives me several ways to form those products. Let's do a little try this with these reactions. And then we got one more thing we'll look at today before we call it quits. Feel free to use your notes. Let's come up with the reagents for these three. Feel free to use your notes, talk to your neighbor. Think about what you're doing. Are you adding carbons and nitrogens or just nitrogen? And think about what you're starting with. Is it a carbonyl? Is it a alkyl halide? Is it a carboxylic acid? And some of these have more than one right answer. Okay, let's take a look. Okay, in the first one, we're going from a carbonyl to the amine, right? For the carbonyl to amine, the one we want to look at is reductive amination. Right, it's reductive amination because we have a double bonded electronegative atom and we're going to a single bonded, right? So here, NH3, right? Since we are just having, we're ending up primary, so we want to start with the ammonia, and then the sodium cyanoborohydride, right? And a trace acid. We could have also done this as 2 steps. So I could have had 1, the ammonia and trace acid. And then second step, I could have added hydrogen and palladium on carbon, right? Or platinum. So I could do it in 2 steps, make the imine, or I can do it all in one pot. Okay, one pot means one process. Okay. Questions about this one? For the second one, we've got an electrophile, secondary electrophile, not that great for SN2, but not bad, right? We're not talking tertiary. So therefore, any of the SN2 style processes could work here. So in this one, I've got two good answers. One is going to be to do the azide, right? So make the azide and then reduce the azide. And here I'm reducing it with the sodium, lithium aluminum hydride. You could have reduced it with the hydrogen and palladium. But I could have also used the Gabriel synthesis, right? And for the Gabriel synthesis, right, I would want to add, now in this one, it's a little bit different. I can show it this way, right? With the negative already there, or the way you usually see it is this and the potassium hydroxide. And sometimes I'll write out succinimate, right? So it'll be succinimate potassium hydroxide. That forms the base reacts with the bromide. Then I need to either hydrolyze that off, or I can use the hydrazine, right, to get me to my product. So actually 2 main methods here, 4 derivatives. So the first one could have had hydrogen and platinum as the second step. The second one could have had hydrolysis, acid and water, followed by sodium hydroxide. Okay, questions about this one? Yes. No, NaCN would add a carbon, right? So if I did this, right, followed by the lithium aluminum hydride, then I would end up with this amine, right? So the nitrile adds a carbon and the amine, right? Where the azide and the Gabriel only adds the nitrogen. And then the last one, this one's a little different because it's in a reverse order, right? We have the amine. Now we could have just added this and that. But what did we say about this reaction? Would this be a good synthesis? It could give us a product, right? But it could also do what? It could just keep adding until we get to the quaternary salt. There is a way that we can go directly to this in good yield, and that is to add the chloride, right? The acid chloride, that'll make the amide, and then I can reduce that amide So let's look at that one. So here I've got the nitrogen. I add the chloride. All right, I make that amide, and then this amide I can reduce to give me the secondary amine now selectively without any other reactions. So if we go up here, right? So the first one's kind of a poor synthetic strategy. The second one is a better synthetic strategy. The way that works is I make the amide. So all I'm doing here is inverting what I showed you before and then reducing that. Before I showed you the chloride side of it, adding the amine. Here I'm showing the amine, you add the chloride. Okay. Okay, acylation of amines. We saw back in previous, if I want to do this reaction, that if I tried to do it with the normal reagent, right? So nitric acid and sulfuric acid, I would end up with a meta derivative because the first thing that happens is that I protonate my amine. Right, so I protonate the aniline, that makes it a meta director, and I get the nitro in the meta. So we know this won't work. So what I can do is I can acylate amines. And so by acylating amines, I can protect those amines. Right, so if I take this and react it with acyl chloride, right, sometimes you'll see pyridine in here or triethylamine. Now I have this group, right, the amide, it's not as basic. So now when I do my nitric acid, sulfuric acid, I can get the para. Right, and then I just need to hydrolyze that off. And then follow up with a mild base. So the acylation is a protecting group. So I turn the amine into an amide, right? Therefore, it's not as nucleophilic, it's not as basic. I can do another reaction, especially something that might have the presence of a good nucleophile or an acid, and then I can regenerate that by hydrolyzing the amide back to the amine. Okay, questions about that? All right, I'll post another homework